Good morning, friends. Today we will be discussing how to assimilate whatever we have been talking so far and add few new things. One of my students, he literally complained. He told me, sir, it gives me an impression as if we are doing flight mechanics. I do not see anything wrong in his statement. When you want to cover aspects of design, initially we cover the approach how you do the conceptual design without using much of a formula, more of physical understanding and statistical data, right? Now imagine aircraft has engine. We have to talk about engine. Aircraft are different types of engine, from propeller to jet engine. When you talk about jet engine, you talk about the intake. It has fuselage, it has wings, structures. It has a layout, a cabin layout, and the passenger will be sitting, that layout, the landing gear, so many things. And each of these subsystems requires a special treatment. But in the first level course, what we are trying to do is use understanding of the physics behind aircraft design and use as a complementary statistical data and see whether you can conceptualize an aircraft configuration or not. Once that is done, then comes the analysis, right? And it goes on, testing, revalidation, reconfiguration. It's a mammoth task, right? But only those who would be able to handle this huge exercise, who are clear about what they are doing, both in terms of statistical data usage and as well as correlating those with the physics of the situation. So today I thought we will discuss few issues, and in the process we will revisit few things, and we will also add some new things, right? Let us see what is our aim. We started from a mission requirement, right? Okay. There are multiple mission requirements. And first thing we did was, we selected, or we should select a baseline airplane or aircraft. That is, see from the history of aircraft available, which aircraft suits your mission requirements, right? So that will become your guideline aircraft, and you can cross-check the dimension which you are conceptualizing. In doing that, first we estimated W0. It's a very gross estimation. What we did, we said, okay, there are primary mission requirements, takeoff, climb, cruise, etc., etc. And then we said, okay, W0 takeoff is some number. And in this exercise, we also estimated what is the empty weight fraction, what is the fuel fraction. A few we have taken statistically, few we have used physical understanding, like for range, for loiter, for endurance, etc. we have done. And finally, we estimated W0 takeoff, the gross takeoff weight. And in that, we ensured that whatever W0 available here, W0 available here or required here, we translated back to W naught takeoff because we have to add that fuel which has been consumed. This we are expert in that. So W naught takeoff we have estimated. Now the next question was on the thrust loading. Thrust loading also from 2-3 criteria we found out what is the thrust loading. Let's say it is 0.4. Some values we have already estimated and we have discussed about what should be our understanding to get T by W, because T by W will play important role in accelerating the airplane from here to take off as well as for rate of climb. We also know that when I am talking about T by W, when I try to write T by W takeoff, I know very well as the airplane is climbing, weight is going on reducing, even the thrust is going on reducing, thrust available because of density effect. And if it's a propeller driven airplane, the dynamic thrust we have to talk about. Similarly here, and again we have given a correction and said, okay, what should be T by W takeoff? Let's say this number is known. Then we talked about W by S takeoff. And there we had different mission, let's say as far as V stall is concerned, climb, rate of climb is concerned, let's say cruise is concerned, right? So let's say we have got here 50 kg per meter square. Here we have got 100 kg per meter square. And let's say here it is 75 kg per meter square. Now the question was, which one should I pick? Ideally speaking, everybody will recommend you take the lowest W by S. Lowest means your wing area relatively is large and it will support lifting characteristics. But then you also understand if wing area is large, drag penalty will be there, right? Turning will be another issue we have to look for. Weight we have to look for. But more than that, what we look for is when I am designing the airplane, what this airplane is supposed to do for the maximum time. If it is a transport airplane where we give more weightage to the cruise, the range, and from that, if I get cruise is around 100 kg per meter square, then I am tempted to pick this value, 100 kg per meter square. Why? Let us see. If I take the lowest based on the V stall criteria, 50 meter per kg per meter square, and cruise says it should be 100 kg per meter square, what is the meaning of that? Let us see. For cruise, lift equal to weight, and so half rho V square S CL equal to W, or W by S is equal to half rho V square CL. This is cruise. And when we have derived this 100 kg per meter square, in the cruise, let's say we have assumed that thrust required minimum is the condition for which CL was under root CD naught by K, and we have already assumed some aspect ratio, and CD naught typically you can assume around to start with 0.021, 0.025 even. The problem is, if I pick W by S equal to 50 kg per meter square, which has come from V stall criteria, that means what? That means if I pick this, then how cruise mission is going to be satisfied? So 50 kg per meter square, if I put it here, of course we'll need to multiply by 9.8. Now you could see that I have to increase the dynamic pressure because CL is fixed. CL is CD naught by K. That in turn tells me that I have to, instead of 100, if I want to make it 50 kg per meter square, so this will demand that you can fly at CL equal to CD naught by K at a lower speed or at a lower dynamic pressure. Then you can maintain that thrust required minimum condition. I repeat, suppose For cruise W by S, we are getting around 100 kg per meter square for our thrust required minimum condition, but we have taken 50 kg per meter square satisfying stall conditions. And if I use that, it means now to have the same condition, I have to fly at a lower dynamic pressure. Lower dynamic pressure means higher altitude and lower speed, or both. Then you have to do a tweaking. Okay. But instead, if you do the reverse thing, what you do, you take W by S, the cruise value, because you say my main mission is cruise, so I will take this W by S cruise 100 kg per meter square. Then what is its implication on this condition? It means instead of W by S, which was 50 kg per meter square, now it is becoming 100 kg per meter square. But please understand, W by S in a consistent unit, it should be Newton per meter square. You have to multiply by G. So instead of 50, we have taken 100. That means what? That means the V stall, which is 2W by S by rho CL max, this condition of 50 kg per meter square was arrived with the W by S 50 kg per meter square, and V stall you got for a particular value of CL max. Because there is a restriction on Vs, which is Vs should be less than 50 knots or some number. If I now design the aircraft so that W by S is 100 kg per meter square, then your V stall will increase. And V stall increases means V takeoff will increase, V landing will increase. That you perhaps cannot afford to do it. So what is the thought process comes? Okay, I'll keep this 100 kg per meter square suitably converted to Newton per meter square by multiplying by 9.8. But then I have a restriction of Vs to be less than 50 knots, so I will change the CL max value, I'll increase CL max value. That means I have to look for an aerofoil whose CL max is higher, and I have to look for another high lift devices which can enhance the CL max locally during the takeoff and after it goes back. So all these combinations we'll be trying, right? And that is how you compromise every factor and find out, okay, this is optimal for me or adequate for me. So this sort of a conflict will come, and a designer's job is how to give weightage to different segments and come back to a compromised, or all people will agree, okay, this is fine. Right? I thought first I will explain you that. So there, after W naught estimated, and once we have frozen okay and given justification, W naught by S, I picked up a number, and I have already picked what is W naught, so I know what is S. So I know what is S wing. This is known to me. And remember, when we were calculating W naught, we also assumed some aspect ratio of the wing, right? And let's say that aspect ratio I have taken around 8, just giving a number, which already you have used while calculating the fuel consumption during loiter or during range estimation. Once you know A aspect ratio 8, then you just start doing what should be the span, what should be the chord. These are all conceptual, right? And then you ask yourself, okay, I want to reduce the induced drag, so my wing should have some sort of a taper ratio. Maybe taper ratio of the wing I'll keep around 0.5. At a conceptual level, not a bad assumption. Then at a conceptual level, I will know that, okay, I need to design a wing so that I ensure that the root part stalls earlier than the tip part. So I may give a washout, that is, I will give some setting negative angle at the tip. So let's say that twist roughly twist maybe 3 degrees down. These numbers come from the historical data, right? Because you are not doing analysis now. Please understand, these are your starting numbers. Then you will do analysis and see whether 3 is required or 3.5 is required or 4 is required or 2 is required or at all not required. Because you have another option, you may select different aerofoils at different sections, having different CLmax and alpha stall characteristics. Then also you ask yourself, am I really giving a sweep? If it is a sweep, then to avoid tip stall, what do I do? All those questions you ask here, right? So in a nutshell, at a conceptual level, you have got an idea about what is the wing area and what is the mean aerodynamic chord, right? You know that how to calculate mean aerodynamic chord once you know the taper ratio. Okay. Now, your wing area, aspect ratio, etc., you have conceptualized. Next question comes, what should be the fuselage length? That is the next question comes to you. What is the fuselage length? And you know, last class we have shown a very good correlation, fuselage length as A W naught to the power C, very good correlation with the gross weight. And we have demonstrated for Cessna 206 and Sinus 912 how accurately it predicts. And you now, by that you have got some fuselage length. So roughly you know, okay, this is the fuselage length I will be operating, right? Next question comes, out of this fuselage length, where will be the expected CG? Generally, I have shown you in the last class for a conventional airplane, it is not a bad idea to assume the CG to be around 25 to 30% of the total length from here. Because the CG is extremely important, because whole of your airplane installation of wing, tail, everything will depend upon why the CG, because it has to define some stability criteria. It satisfies some stability criteria. The majority of the work, or majority of the iteration works out here, because at this stage you do not have an idea about what sort of weight distribution will happen. So once you conceptualize, then you use approximate correlated data, statistical data, and see where the CG should be. But not a bad idea if you take this sort of a percentage of CG total length. Now once I do this, now what are the information I have got? Let us see. We are all talking about conceptual design. So we know what is W naught, we know what is the wing area, we know what is the wing aerodynamic chord. Our next question would be, and also we know what is the fuselage length, right? So let us say this is the fuselage length. And around 30% I have kept the CG, right? What I prefer to do, let's say I am designing a symmetric wing. So initially I will try so that the AC of the wing and CG are at same location. That means this wing will only be responsible for producing lift. I have taken symmetric wing, so there are no CMAC which are negative, right? I am making life simpler. I put AC of the wing and the CG of the aircraft at same point, so this wing lift will not create any either a destabilizing or a stabilizing moment. Next question is, how much is the tail size, both horizontal and vertical, right? That is our question. Tail size as well as where do I locate the tail. Do not forget that we know now what is the fuselage length. Right? We know the chord, we know the wing area. So to have an idea about what should be the size of the horizontal tail to start with and its location, we have given you some guideline where we all know by understanding physics the tail volume ratio, which is St LT by SW and C bar, that plays very, very important role. And you have seen very cleverly I have put AC of the wing and CG at same point, so that wherever I am putting the tail, horizontal tail, the AC of the horizontal tail and this distance, which is CG of the aircraft as well as AC of the wing, so this I am defining as LT. Theoretically, conventionally, LT is the distance between AC of the tail and CG of the airplane. Okay. Now, before I talk about VH and all, I decide as far as horizontal tail is concerned, we use symmetric aerofoil. For wing, we use mostly cambered aerofoil. Although example I am giving symmetric so that there are no other complications to start with, but horizontal tail it is symmetric. And also in horizontal tail, the aspect ratio of the tail should be less than aspect ratio of the wing. That you know the reason is because we want that the wing should stall earlier than the tail, so that there is some control left here. And as aspect ratio decreases, the self-induced downwards also increases, so it stalls later. All those understanding you have got. So let us say I take from historical value, I take aspect ratio of the tail, maybe 4 or 5, right? Once I understand the importance of VH, I use statistical data and check for what type of airplane I am designing. And let us say I am designing a general aviation. And if you see my last lecture, for general aviation, the VH, which is in the Raymer's book, it is written as CHT. This value is around 0.7, little higher side. Okay, but okay, at a conceptual stage, you must use these higher values. So what is the meaning of this CHT, which is nothing but basically VH, that is 0.7. So that is equal to ST into LT by S wing CW wing. What is our aim? Our aim is to see what is the tail size. But by now you know this value you have estimated, this you have estimated. You now need to estimate ST into LT. So you get that value as 0.7 into SW into CW bar. So this value is also known to you. How much is ST into LT, right? And for LT, you have another guideline based on statistical data. Refer my last lecture. It says for front mounted engine, LT you can take as 60% of fuselage length. Similarly for wing mounted, some variation, 55% is there. But when I do, I take LT as simple as 65 to 70% of fuselage length. So you can this take 60 or 65%, 70%. In fact, you should have various combinations. So I pick one of these number, and you know fuselage length, already you know that. So LT is known to you. So ST into LT is known. Now LT is known, so you get ST. So now you know where to locate the horizontal tail and what would be its area at a conceptual level. We are now doing analysis at this point, right? This is where the starting point. So once I do that, then natural question comes, what will be the vertical tail size? Please understand, again and again I am repeating, these are all conceptual numbers. We are not doing analysis. I will tell you how to graduate from here to the analysis so that you are perfect in your estimation. For vertical tail, we follow the same. There we use the coefficient CVT, which I have given you last class. Say for general aviation it is 0.04. Please also understand, when you define CHT or tail volume ratio, we defined as ST/LT by SC bar, but for vertical tail we defined as ST/L vertical tail by S wing into span of the wing, right? So that is why the order of magnitudes are different, okay, right? So once I know CVT, so I write 0.04 equal to, let's say I picked 0.04, that's equal to S vertical tail, L vertical tail by S wing into span. And you know that I know SW, I know span of the wing, so I again get SV LV equal to 0.04 into SW into span. So this number is known. So I know SV into LV. Now the question is LV equal to LT? And you could see that for an airplane, if this is the empennage, some configuration will have horizontal tail here and vertical tail is starting from here. So naturally, if this is the AC of the vertical tail and CG is here, then LV and LT are not same, right? But at a conceptual level, we will say, okay, both are same. I will not bother much. So in a sense, I am telling LV is also known. So I easily get what is SV. The vertical tail area also is known. Once I get this number by this, then we cross check for a given airplane what is the vertical tail area ratio with respect to the wing area. That is, what is the ratio of vertical tail to wing area, what is the ratio of horizontal tail with wing area, and I must see that for this type of airplane whether this ratio is coming closer or not. Okay? Yeah, we have spoken about horizontal tail and vertical tail, but if you see a horizontal tail, there are elevators. Question would be, how much would be the elevator size for a given horizontal tail area? This is horizontal tail, right? You will find for most of this airplane, this elevator and rudder you understand, if this is the vertical tail, you have a rudder somewhere here. So typically elevator and rudder are 25% to 50% of tail chord. That is, the meaning is, if this is my horizontal tail, you will find if this is 50% line, so around 25 to 50% area is kept for elevator, right? There are finer things which you will see once we analyze it. Yes, I am taking, let's say I am taking 50% of the horizontal tail in terms of chord. This part is my elevator. I may have elevator something like this. I may use only 90% of this as an elevator, because I know there are tip losses here, so I may not use it, right? And there are other issues in elevator you will find. that there's something called flutter at high speeds. You could see that if this is the elevator which is supposed to move about this hinge line, its CG is behind, so it will have tendency to do like this. So for that, we also do some other balances, we call aerodynamic balance, mass balance. In a sense, we want to see that this effect is neutralized. We will talk about those things. We have spoken that in our stability classes earlier, but this is for the conceptual. You need not bother about those things. You are more bothered about how much should be the elevator area I should keep once I have got a horizontal stabilizer area. That's all, right? So the answer is simple. You take a 50% line, the cost should be between 25 to 50%. So initially you take around 40%. How does it matter? Or make 3 configurations. One is 25%, one 40%, one 50%. And then anyway we will be doing analysis to see which one is better suited, right? Similarly for rudder, you will see that for high speed rudder, high speed airplane, rudder will be around, this will be around 50% of the span. And as far as the chord is concerned, that is whatever I have told you earlier, that 25 to 50% of vertical tail chord. But you will find for the high speed, around 50% of that vertical span is used of vertical stabilizer as a rudder. In a rudder, there are many other things we will be discussing. How to ensure that it has better spin recovery qualities, which comes into the final design or a second stage design. At a conceptual stage, I need to have those numbers, right? Okay. Now coming back to other control surfaces, at a conceptual stage, we have wing, and you know roll control is done by aileron, right? And in aileron you will find the aileron span would be 90%. Total 90%. You have seeing airplane where 90% of the span is used as aileron. This percentage is again not used because of, you know, there are tip stalls, the vortices will be there, so effectiveness may not be good. But you will also remember you need to have space for flaps which are high lift devices, right? So now then what happens, then your wing layout changes. So you say this is center, some portion you are using for high lift devices and the flaps, and rest portion you are using as aileron. So this is aileron, and these are high lift devices. The question is, how do I decide at a conceptual stage the aileron size? You can use historical trend, again from Raymer. I will be giving you some number for a typical airplane, you will realize then. So if let me draw this, 0.2, 0.4, 0.6, 0.8. This is aileron span by wingspan, and this is aileron chord by wing chord. The historical trend is something like this. something like this. Okay. How to use this? Of course, these values are, please refer those charts from book or from any other literature. Here, what we were looking for, how do I size my aileron? If this is the wing, one thing I decide first, what should be the flap space to be kept. Once that is done, so you have got this much of space for the aileron. Okay? And typically you will find aileron span will be 50% to 90%. When I say 90%, you can easily understand that means there are no high-lift devices, right? 5% left here, full is aileron. But when I am using flap, so you are more close to 50%. So if I have that aileron span to wingspan, this ratio I will be knowing. Once I pick a number from here, then I know this ratio, and I can easily, suppose the ratio is coming 0.6, so I come here and somewhere here I see what is the ratio of aileron chord to wing chord, and since I know wing chord, I can also find out what is the aileron chord from here. This also gives you quite a good estimates at a conceptual stage. Also understand for a high-speed airplane, if you are using a conventional aileron like this at high speed, it may happen that you are giving a deflection down here, up here to bank like this, but because of high speed, this wing may twist downward, right? It may generate twisting moment. And then instead of banking towards left, it may start banking towards right. We call it aileron reversal. So for high-speed airplane, you'll see people use spoilers. Spoilers are, of course, required for spoiling the lift. Conventionally, they are used for landing. But now you could see that if I reduce lift on one side of the wing, so I'll be able to generate a bank angle and will avoid high-speed aileron reversal. So all these combinations are used, and generally these spoilers are installed. So this is the wing, and this is the line of maximum thickness. The spoilers will be installed aft of the point of maximum thickness. So all those details we will be talking later. However, you must understand, since the physics behind spoilers giving a rolling moment is based on spoiling the lift, that effect is nonlinear. So these are for small corrections, right? One has to have a very good flight control system to manage it smoothly. By today's lecture, I tried to summarize at a conceptual level how can you think of an airplane without having much of a formula, right? But at the same time, you should understand, I need to also know how effective should be my elevator or rudder so that I can trim the airplane from one condition to another condition, right? What should be my elevator size so that I get right type of elevator control power. So this part I will talk tomorrow. I will start with an example, a numerical problem, and then come back and try to see how we can translate those understanding into the design of an elevator. Similarly, rudder as well, right? Thank you very much.